My name is Caleb Flint, and this is my Lab 3 magnetic field of a bar magnet. So for the introduction and results, the purpose of this lab is to explore the concepts of magnetic fields by measuring to determine the magnetic field's dependence on distance, which will then be compared and visualized with a computational model using the Biot-Savart law. Some results here on the right side. For the experimental dependence, it was found to be negative 2.8758. The magnetic dipole was found to be 3.307 AM squared. In the computational model, is shown to mirror the data collected and calculated with little to no differences. We'll get to that in a minute. So some fundamentals for this experiment. I try to get some of the best images of the formulas because putting formulas in Google Slides is terrible. But for the distance dependent, B bar, which will be equal to KR to the power of N, and ln Bx, which will be equal to ln K plus N times ln R. And the Biot-Savart law is shown there in the image below. These are some formulas we use for this. So here is the data we collected in Excel. If you want, you could pause to view this a little bit closer. So there's all of this. We have at the bottom the off-axis field and all the averages and everything calculated. And over here on the right, we shown the graph on the ln Bx line, ln R line. And the y for it is found to be negative 2.9647x minus 14.73. So for our observation, when the magnetometer is far away from the magnet, it just measures a value near zero for magnetic field in the x-axis. And as the magnetometer moves closer to the magnet, it shows that the measurement of the x component of the magnetic field go up. So some calculations for this experiment: the distance dependent using the line of best fit equation, n equals slope, which is equal to 2.8758, and the magnetic dipole moment, ln K, which is equal to negative 14.554. K is equal to 4.778 e negative 7, and the U involved, it's that weird looking U, I couldn't really find it. But anyways, is equal to 3.307 AM squared. All right, so here is some of the coding that we had to do in Python using the starter equation given in the lab experiment. If you want, you can pause to view. I will try to put the GlowScript link down in the description if you want to be able to click and view that. So here's the first part, or the first half. And here is the second half of the coding involved. And here is the computational model involved after you run the code. And it shows you the moments and all the values calculated down at the bottom. Pause to view if you want. So for the discussion in our video, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? For this experiment, of course, I did not account for the Earth's magnetic field, which would have drastically changed a lot of the values collected, shown throughout. Instead of looking at the magnetic field of the bar magnet, it would have been looking at the interactions between the bar magnet and Earth's magnetic field, causing the X involved to not start at zero in the experiment. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? For this, the two magnets involved stuck together would combine to make a more powerful magnetic field. The total magnetic field would have been doubled.